Hello, I'm Harry Commin with Enclustra in Zurich, and thank you very much for joining me for this short presentation about our new digital signal processing library for FPGAs. So, in this presentation I will briefly say who Enclustra are and what we do, and then I'll introduce our new DSP library for FPGAs. And I'll spend most of the presentation doing an on-screen demonstration where we'll build a simple DSP system in Vivado, we'll run it on hardware, and at the end we'll look a bit at how to model that system in software. So what is Enclustra? We're an FPGA design house with a bit more than 50 employees, with our headquarters in Zurich, but with branch offices in Germany, the USA, and China. We are interested in all aspects of FPGA technology, from the hardware to the HDL firmware to the embedded software. And we produce a wide range of FPGA and system-on-chip modules, like this roughly credit card-sized form factor and this laptop RAM module form factor. And we also make baseboards to plug those modules into. But we don't just make hardware, we also make IP cores for FPGAs, and that's what I would like to talk about today. So, what is our universal DSP library about, and what is the problem that we want to solve? Well, over the years, we've found that many digital signal processing systems use the same functional blocks. This is not only DSP blocks like FIR filters, IIR filters, CIC filters, mixers, codecs, and so on, but also simple glue logic like multiplexers, demultiplexers, buffers, interface converters, and so on. And this should be a good thing. It should mean that we can reuse code and reduce our development cost and risk. However, what we find in reality is that even minor differences between different projects can lead to major extra development effort. For example, a block capable of processing multiple parallel channels may need significant changes to instead process time division multiplex channels. Another example is perhaps we develop a block suitable for using in a continuous wave processing system, but then we want to use it in a pulse processing system where we need to reset some state between bursts. Even something as simple as converting between real and complex signals can potentially waste hours of development effort. Another issue we see often is that the interface conventions used in one project may not be compatible with those used in another project. For example, one project may use flow control and another doesn't. So all these issues add up to mean that too much time is spent implementing the most common DSP functionality, when really we would prefer to focus our effort on the more critical and challenging functionality specific to each project. Of course, this problem has existed for decades, so why do we think there's an opportunity to fix it now? Well, one reason is that FPGAs are getting better. So we're increasingly finding that many customers would prefer to sacrifice some small amount of FPGA resources or timing performance or power consumption in order to reduce the overall development cost and risk. Of course, we can still handwrite highly optimized DSP blocks at a higher development cost whenever they're needed. But if we can afford to use a little bit of logic to unify our interface conventions, then in most cases that extra cost will be negligible compared to the saving in development time. A second reason to be optimistic is that graphical design tools are also getting better. So, for example, using Vivado's IP Integrator tool, it's realistic to imagine clicking together those common DSP functions very quickly, even if some critical project-specific processing needs to be handwritten and added later. Obviously, we are not the first to recognize this opportunity. A lot of large companies are already going down the route of graphical development. For example, Xilinx already offers a lot of IP cores that can be used in their IP integrator, so this would be the most obvious solution. However, we generally find that the DSP blocks that we need are not available, and the blocks that do exist tend to have subtle differences in their behaviors that make them difficult to use together. Another option could be MathWorks HDL coder with MATLAB and Simulink. The main barrier for us is the high license cost that usually our customers would prefer to avoid. Another problem is that after each new version of Vivado is released, it takes some time for those updates to be integrated into any third-party software. Another graphical tool that I've worked with is LabVIEW from National Instruments. This option is only really feasible if you make a long-term investment in NI hardware, which is not generally suitable for us. So in the end, our decision was to create our own solution, and that's what ENDSP is. I think the key to finding something that worked well for us was that one of our engineers was able to design an interface convention that is simple enough to be easy to use, but still general enough to cover the vast majority of use cases. This means each block can support parallel and TDM channels, continuous wave and pulse processing, and real or complex signals. ENDSP is fully integrated with Vivado's IP integrator, so every block is provided not only as raw VHDL code, but also wrapped up in a graphical IPI block. And we look forward to supporting other FPGA vendors if they produce their own graphical design tools at some time in the future. Another strength of ENDSP is that it makes extensive use of free open source code libraries from PSI, which helps us to keep the costs as low as possible. For example, these libraries provide a lot of the underlying code we need for creating bit-true fixed-point software models and for packaging the Vivado IPI blocks. So now that the introduction is done, let's move on to the demonstration. What we're going to do is build a simple digital down converter in Vivado. We'll just extract two 1 meg complex basebands from 4 parallel 100 meg input streams. So on the input, we have 4 independent channels of 16-bit real-valued data arriving at 100 megasamples per second. The processing clock will only be running at 100 MHz, so these 4 channels must run in parallel. Then we mix all 4 channels to 2 complex basebands at 20 MHz and 25 MHz. The 2 mixers each output 4 channels of complex IQ data, so 2 mixers times 4 channels times 2 complex components gives us 16 parallel components at 100 megasamples per second. Next, we have a CIC decimating filter which decimates by a factor of 25. So at the output we have 16 parallel components at 4 megasamples per second. 16 times 4 is only 64 megasamples per second, which is less than the 100 MHz clock rate, so now we can interleave all the channels and all the complex components into a single time division multiplexed stream. Finally, we have an FIR filter which acts both as a CIC compensation filter and as an anti-aliasing filter for the final decimation by a factor of 4. We don't care too much about the specific requirements of this filter, but let's just assume that in the design phase we calculated that 80 filter taps would be required. Now, the output rate is 1 megasample per second, so if we think in terms of multiply-accumulate operations, then this filter needs to process 16 channels times 1 megasample per second times 80 taps, which is 1.28 gigamax per second. So we just need to be a little bit careful. We can't just use one serial multiplier because on a 100 MHz clock, that will only give us 0.1 gigamax per second. We could run the 80 taps in parallel, but that would give us a processing capacity of 8 gigamax per second, which is a lot more than we need. So a more efficient approach is to instead run the 16 channels in parallel, which gives us 1.6 gigamax per second. So without further ado, let's open Vivado and create a new project. I'll just call it Demo Project. And I'll select the Spartan 7 module that I'm using so the settings and constraints are set up correctly for the board. So we need to create a block design in which to build our DSP system. First, I'll very quickly add a clocking wizard so we can configure a processing clock. We don't need to handwrite any constraints because they're automatically inherited from the board settings. And we can just keep the default 100 MHz output clock. And finally, I'll create a port to connect to the reset button on the board, and another port to connect to the external clock, which on this board is 12 MHz. So we're almost ready to start placing some DSP blocks, but first we need to tell Vivado where to find the DSP library. So we open Project Settings, IP, Repository, and set the path. Now if we open the IP catalog and expand User Repository, User IP, then we can see that all of the DSP blocks are now available, and we can start by placing a mixer block. In fact, we need two mixers, so I'll just copy and paste. And this first mixer is going to mix by 20 MHz, so I'll just rename it to Mixer 20. And then the second mixer will mix by 25 MHz, so I'll name it Mixer 25. Next, we want to place the decimating filter chain, so I'll just click on the plus icon to add a CIC filter. And I'll also add the FIR filter. So now we've added all of the DSP blocks that we need, and now it's time to configure them. So we'll just look back quickly at the requirements. Okay, so on the input side we need 4 channels in parallel, and they're each 16-bit real valued. And on the output we have parallel channels, parallel complex components, and they're each 18 bits. For fixed point numbers, we use this 3-part notation for sign bit, integer bits, fractional bits. So 1 plus 0 plus 17 is 18 bits in total. The default mixing frequency is already 20 MHz, and we can just set the phase to 0. For the second mixer, all of the interface settings are exactly the same. But we just set the mixing frequency to 25 MHz instead of 20. And the mixers are done, so we'll move on to the CIC filter. So firstly, the CIC decimation ratio is 25. We have 8 channels, which on the input side are parallel with parallel complex components, but on the output side they are interleaved TDM channels with interleaved complex components. And finally we'll configure the FIR filter. Okay, so the FIR decimation ratio is 4, there are 80 filter taps, and we want the channels to be processed in parallel. And I'll just paste in some filter coefficients that I've pre-calculated, for example in MATLAB or Python. ENDSP supports human-readable decimal numbers, so there's no need to convert these numbers to binary. It's worth mentioning that these are default values, and in this short demonstration we'll just use defaults to configure every block. But in practice, if we need runtime configurability, then we can enable a register bank on every block by clicking this checkbox. And as you can see, this causes this AXI light interface to appear on the block, which can then be connected to your register interface. Let's quickly finish configuring the FIR filter. 8 channels, interleaved TDM on both the input and the output. So we've finished configuring all of the DSP blocks, but we can't quite connect them all together yet because we have 2 mixers that need to connect into one CIC filter. So we just need to concatenate the real and the imaginary streams using a pair of concatenation blocks. Of course, the data widths and channel numbers just need to match the blocks on either side. And we just copy-paste to create the second instance. And now we can finally connect together all of our DSP blocks. Now we want both of the mixers to see the same input signal, so we'll add a stream duplicator block. In order to quickly test our design in hardware, we want to generate some input signals inside the FPGA. And there are a few options available for doing this. Firstly, there's something called a pulse player, which allows us to specify an arbitrary waveform that we could read out of a blockgram in a loop. Another possible option is a noise generator, which is useful for generating wideband test signals. But for this simple demo, we'll just generate some sine waves using a DDS block. We'll give ourselves plenty of bits of frequency resolution. And I'll paste in some pre-calculated sine wave frequencies. It's worth quickly explaining how these frequencies were calculated so that we know what to expect when we run this in hardware. So here are some graphs showing the simulated outputs from our processing chain given the specified sine wave inputs. If we first focus on the left-hand figure, this shows the expected outputs from the 20 MHz baseband. And as you can see, these first 2 sine waves have frequencies very close to 20 MHz, so they are in band for the 20 MHz baseband. And we see these slow varying sine waves in the simulated output. But these second 2 frequencies are very close to 25 MHz, which is out of band for the 20 MHz baseband, so we see 0. And of course we see the opposite situation for the 25 MHz baseband. The first 2 signals are out of band, so we see zeros, whereas the second 2 signals are within band. These specific frequency values were chosen purely for display purposes, so that when we capture a buffer of 1024 samples in chipscope, they will display neatly as 2 full periods, 4 periods, 6 periods, and 8 periods. And this just makes the output a little bit easier to roughly check by eye. So our block design is very nearly finished, and the last thing we want to do is add something to handle the final output. And to do this, we're going to use something called a stream observer, which attaches chipscope probes to the stream so that we can capture its data when the design is running in hardware. The stream observer listens completely passively on the stream, so we also need to add a stream sync so that the output signal has somewhere to go and is not optimized away by the synthesis tools. And the block design is basically finished. I'll just fast forward now through the boring part where I attach the same reset to every block and the same clock to every block. And we're done, so I'll validate the design to check there are no errors. And finally, I'll generate the HDL wrapper that Vivado needs to synthesize the top level. As you can see, the HDL wrapper only contains a clock and a reset because in this design, all of the data signals are generated internally and captured internally in the FPGA. We're now ready to synthesize the design and generate the bit stream to program to the FPGA. Obviously this will take a few minutes, so I'll cut the video here. So the build is now finished and we're ready to program the FPGA with the bit stream that we generated. I'll just fast forward through this part where I choose which signals I want to display in chipscope. We just want to plot the real components of the final outputs, which should match with these graphs that we looked at earlier. Okay, so the wave window is now set up how we want, and the design is already running in the FPGA, so I'll just click this play button to capture data from the FPGA. As we expected, 4 of the outputs are just zeros, corresponding to the 4 out-of-band signals, so I'll just delete those ones. And the remaining in-band signals are roughly what we expected, 2 periods, 4 periods, 6 and 8. Although these results look roughly correct, we would of course like to confirm that they are exactly what we expect. And the way we can do that is by using bit-true simulation models. Every ENDSP processing block is provided with a fixed-point software model that can be used to verify the design both in HDL test benches and by capturing data from hardware. We don't have enough time to go into detail, but basically we just need to configure the blocks we use, construct the models, and then simulate the processing chain. And then we can numerically compare the simulated outputs with our HDL test benches or hardware captures. As you can see, the models are written in Python, but they can also be called from MATLAB using MATLAB's built-in Python support. So just to very quickly summarize what we've done, we built a very simple DSP system in Vivado without writing any new HDL code. We ran our design in hardware, and we very roughly verified the hardware output against a bit-true software model. And that's all we have time for, so thank you very much for joining me, and I would be happy to take any questions.